You know, in mechanical design, having a powerful motor is only half the battle. The real magic is in the control, the precision. It's all about getting that power exactly where it needs to go, in the exact form you need it. Today, we're sizing up the science behind mechanical drives.
Think about this for a second. One single wrong pulley size, just one miscalculated gear ratio, and an entire complex system can grind to a spectacular, catastrophic halt. We're not just talking about being inefficient here. We're talking about the thin line between a bulletproof machine and a pile of scrap metal. And here's what that looks like. On the left, you see the ugly consequences of getting it wrong. We're talking fractured belts, sheared gear teeth, and expensive, frustrating downtime. But on the right, well, that's the result of precision. A perfectly optimized system, just humming along, delivering power exactly as it was designed to. The difference between these two worlds, it all comes down to the math. All right, let's get right into the heart of it. The core principle behind any power transmission system. Doesn't matter if it's a belt, a chain, or a gear, it all boils down to the relationship between three things: speed, torque, which is really just a fancy word for rotational force, and power. If you can master this fundamental ratio, you can design anything. It all starts with a beautifully simple idea. If we assume there's no slip, the linear velocity, that is the actual speed of the belt itself as it's zipping between the pulleys, is constant. This one single rule is the key that unlocks everything else we're about to calculate. And that leads us directly to something called the speed ratio, which we usually just call I. This little number is what defines how you're transforming the motion. It's simply the input speed divided by the output speed. And because of that constant belt speed we just talked about, this ratio is also the inverse of the pulley diameters. So what's this ratio actually telling us? Well, if that number is greater than 1, you've got yourself a reducer. This means your driven pulley is bigger than your driver pulley. What you're doing is slowing down the output speed, but, and this is the important part, you're getting a huge mechanical advantage in return. You're increasing the torque. This is perfect for stuff like heavy-duty conveyors that need a lot of grunt. And of course, the opposite is true. If your ratio is less than 1, you have an overdrive system. In this case, the driver pulley is bigger than the driven one. The output now spins faster than the input, but you have to trade something for that speed. And what you trade is torque. Think about applications like high-speed fans, where speed is everything.
Okay, theory is great, but let's get practical. To go from an idea to a real-world design, you need the right tools. And for belt drives, that means having a core set of formulas in your toolkit.
What's so powerful about these three formulas is that they pretty much form the entire foundation for your design. That speed formula, it's a direct application of the ratio we just covered. The torque formula lets you translate your motor's power into actual rotational force. And the belt length formula, well, that handles the physical geometry, making sure all your parts actually fit together in the real world.
So let's see how this all comes together in a logical design process. It's basically 4 steps. First, you always start with what you know: your motor power, its speed, and the output speed you're aiming for. From there, step 2 is calculating that ratio and picking your pulley sizes. Step 3 is all about the geometry, finding the belt length and the distance between your pulleys. And then the final, absolutely critical check, you verify that the output torque is enough to handle your load. All right, let's put some real numbers to this to see how it works. Imagine we've got a motor spinning away at 1500 RPM, and it's hooked up to a 120 millimeter pulley. The component we need to drive is attached to a 240 millimeter pulley. So what's our final output speed going to be? We just take our numbers and plug them straight into that speed formula. The output speed, N2, is our input speed, 1500 RPM, multiplied by the ratio of the diameters, which is just 120 divided by 240, and there it is, 750 RPM. It makes perfect sense, right? Because the driven pulley is exactly twice the size of the driver pulley, the output speed is exactly half. This just shows you that brilliant inverse relationship in action. Double the diameter, half the speed. Now, those same fundamental principles of speed and torque also apply when we switch gears, so to speak, and talk about chain drives. But there's a really important difference. Instead of relying on friction like a belt does, chains use what we call positive engagement. The teeth physically mesh together. And that changes one key variable in our math. Here's the crucial difference. Instead of using diameters to figure out our ratio, with chain drives, it's all about the number of teeth on the sprockets. As you can see, it's the number of teeth on the driven sprocket divided by the teeth on the driver. This gives you a rock-solid, precise, non-slip ratio every single time. Okay, so even though we use the tooth count for the ratio, we still need a diameter for things like layout and checking clearances. This is where something called the pitch circle diameter, or DP, comes in. This formula you see here uses P, which is the chain pitch, the distance between the rollers, and Z, the number of teeth, to calculate the sprocket's effective working diameter. So far, we've been living in a perfect world of ideal formulas. But as any experienced engineer will tell you, the real world is, well, it's messy. You've got to deal with friction, shock loads, and inefficiencies that are always part of the equation.
With any drive that relies on friction, like a V-belt, you're going to have some slip. It's just a tiny bit of relative motion between the belt and the pulley surface. You can't really avoid it, and it results in a small loss of speed, maybe a few percent. But you absolutely have to account for that in high-precision applications. Now this is absolutely critical. You can't just match your motor's power directly to your load's requirement. It's a recipe for disaster. Why? Because real-world systems have startup shocks, vibrations, and occasional overloads. A service factor is a safety multiplier you get from a table like this. You multiply your motor's power by this factor to get a design power, which ensures your components can actually survive in the tough real world.
And you've got to remember, no system is perfectly efficient. You're always going to lose some power to friction and heat. V-belts are actually very good, running around 95 to 98% efficient. But synchronous belts, you might know them as timing belts, and well-lubricated roller chains are even better, simply because they eliminate that slippage. These small percentages really start to matter, especially in high-power systems or machines that run 24/7. A successful design isn't one that just works on day one. It's one that works reliably for thousands and thousands of hours. And that means you have to be thinking about longevity and maintenance right from the very beginning. Here are 4 checkpoints that are completely non-negotiable for a reliable design. First, wrap angle. You have to make sure enough of the belt is touching the pulley. We usually want over 120 degrees for V-belts. Otherwise, it's going to slip. Second, for chains, lubrication is everything. It prevents wear and something nasty called galling, where metal surfaces can literally weld themselves together. Third, belt tension has to be just right. Too loose, it slips. Too tight, and you'll destroy your bearings. And finally, material selection. This choice impacts everything from how long it lasts to how much load it can take. So let's just quickly recap the 3 absolute must-know formulas from today. First, the speed ratio, which defines your system's transformation. Second, the torque calculation, which makes sure you've got enough force to do the job. And third, the design power formula, which builds in that crucial real-world safety margin. In the end, it really all comes back to this one idea. A successful mechanical drive isn't the result of guesswork or close enough. It's born from a deep understanding of the principles and a precise application of the math. Precision isn't some far-off goal. It's the starting line.